I want to show you now the Neurthino package. And yeah, it's a little bit of a misspelling, but it's basically the combination of neutrino and earth. Because yeah, now this time it's a little bit closer to what I actually do. So here I showed you the basic principle. So Tamas already told you a little bit about KM3net. So one part of KM3net is actually for neutrino oscillation properties. So, and what we actually do there is, yeah, we have atmospheric neutrinos from cosmic rays. They're propagating through Earth. And then we get them in the detector. And then we want to look for, oh, I think it's a little bit off here. So we want to look for modifications in these in the oscillation probabilities due to the meta effect, which we can use then. So, but in order to analyze the data, we also have to calculate neutrino oscillation probabilities. So we have the path through Earth. So the Earth has a certain density profile, which is mostly modeled after this preliminary reference Earth model, and which is the densities I showed you here over the radius of the Earth. So it's quite, yeah, it's not that simple, this distribution. And in order to do that, yeah, we need first a little bit of math. So I think most of you can follow that. So we have how it always starts with a Schrödinger equation. In order to go then to the right basis, so the mass basis where the Hamiltonian is basically just populated with the mass or with the energy eigenstates, and the flavor basis is a different one. So that's the reason why we have the PMNS matrix. So nothing fancy so far. And in order then to calculate the transition probabilities, we need to employ the PMNS matrix, and then yeah, we can do it like that. So you might ask, so why you then build a whole package around this? This is just a little bit of linear algebra, and Julia is very good in this, so I can just type it down and then yeah. So it gets complicated. Oh yeah, that's basically what you should look like now. So yeah, okay, what's the problem about all this? And yeah, it gets complicated even with these meta effects, which modify the Hamiltonian in the flavor basis. So especially because yeah, it's mostly normal matter we propagate through, so it modifies the electron term in the Hamiltonian. So and to calculate then the transition probabilities, you need to then diagonalize then this modified Hamiltonian, and so you have some more of eigenvalue problems there. So it's also doable, but also to write everything down, it's yeah, very annoying. And that's the thing where this package comes into play. Yes. So, okay, yeah, as I showed you already, it's called Neurthino here also on the slides, and I think I put it also in the Indico, the GitHub link. This is a model for also doing n-flavour oscillation. So in most of the cases, if one deals with neutrinos, you do it with the 3 flavors, but there are also sterile models and so on. So this is, I designed it as a general model. So, and how do you do it? Yes. So we also always start with, we have some package we included, and then we set up our oscillation parameters of the vacuum case we want to use. So for example, you can get the best fit for at the moment from NewFit, and then you set here, oh, this is very annoying to do that off. You set here then also the oscillation parameters. So the mixing angles, then the CP phase, and the delta mass squared. With that, if you're just interested in one probability in vacuum, you can do it like this. So, okay, if I, there's this P nu nu, there you put in the oscillation parameters, then you give it an energy in GeV, and here a baseline, which should be in kilometers, I think. So if I propagate for 10,000 kilometers, and I say, okay, my initial flavor was a muon, and my final flavor is a tau. What is the probability for this? Yeah, you have, you see it here. So yeah, that's the simple case. There's everything done behind the scenes. And now we come to the special case, which to the if the baseline is not just the vacuum or one single density. So what you do here, you can also individually set up your PMNS matrix by the oscillation parameters and the Hamiltonian here. And then with that, you can, for example, calculate these modified matrices, or if we go to the full example about propagating through Earth, then here I set up a range of zenith angles from where the neutrinos come from, and from that I set as in these package also included is this PREM model, and then you can just say, okay, I have these zenith angles. That is the depth of the detector in kilometers. So for KM3 Orca, it's on the bottom of the Mediterranean Sea in a depth of 2.5 kilometers. And you say, okay, I want 100 samples. And here you can also discretize the densities. Otherwise, so it will then follow the path given here and take the densities at the certain points. So it will sample them. And if you don't discretize then the densities in a certain way, it will calculate for each one. And if you do this, then it will look what is the next one given in this range and do it for that. Okay, I give also here an energy range from 1 to 100 GeV, and then I calculated this. And then if you plot this, this comes out here, for example, for electron or electron neutrino over the given zenith range, and as I said, these energies. So yeah. This also leads already to my summary. So it's actually, first of all, the most important thing that it's working. So you saw the oscillogram. So also the oscillogram on the first slide was generated with this. And it's also out of the box n-flavour, because what I also compared here, this is a benchmark to others. So I think Newcraft is a pure Python package, which is far off with the performance. The green one is Neurthino, and the blue one is osprop. What we normally use in KM3net. This is in C++, and what the point there is, I compared here the 3-flavor case. And for all the different cases you have there are different classes with certain optimizations. So if we would go then to the 4-flavor case, this would also look certainly different. So at the moment, it's still factor 3 slower than osprop, but there are still improvements which can be done. So yeah, it also includes these PREM models, so you don't have to look up what are the densities to the Earth. Also, if you have a certain baseline from an accelerator to an experiment, so, and depending on the depth, you also could look up what is then the Earth density for this baseline. And what's still to do is, first of all, I normally put in the Schrödinger equation, but for there are some models where you need the formulation in Liouville von Neumann, for example, for some decoherence effects. And then in order to make this gap not happen at all, or at least smaller, what one could do is do an interpolation of the oscillation parameters. So to reduce the number of eigenvalue determinations you need to do. And also one could go for a GPU. But yeah, that's it so far, yes.